Let's consider fusion and energy produced by fusion and amount of solar material as we go through this problem. We're going to assume that we simplify the fusion process and just say that 4 protons fuse and form a helium nucleus, and there's 26.7 MeVs released. There are many more details to this. We're not going to cover those details. We're interested in the energy situation. So how many fusion reactions per second are required to provide this observed power? The luminosity of the sun, 3.85 times 10 to the 26 watts. 3.85 times 10 to the 26 joules per second. So how would we go about that? Well, we can work with this energy, 26.7 MeVs. Let's find out how many joules are released in one fission reaction. Let's convert the MeVs to joules. 1.6 times 10 to the minus 13 joules is 1 MeV. And that tells us that from one fission we get 4.272 times 10 to the minus 12 joules. That's from one fission. We need to produce this much energy each second, 3.85 times 10 to the 26. And this 3.85, this is the visible luminosity. This does not include neutrinos. But just a rough ballpark estimate. So let's see what we have here. This 3.85 times 10 to the 26 joules per second, and we have available 4.272 times 10 to the minus 12 joules per fission. So the joules will cancel here, and we'll have fissions per second. So you ought to check this on your own calculator. 9.01 times 10 to the 37th fusions per second. And that's the whole process of the 4 hydrogens fusing into helium. So that's the number of fusion reactions per second. We found the number of fusions, or how much energy for one fusion. We divided that amount into the visible luminosity of the sun, and we find the number of fusions that are occurring per second. So part B, how much does the sun's mass decrease in 1 year? How much will the sun's mass decrease in 1 year? Well, we can calculate how many joules per year the sun is releasing to space in visible radiation and the nearby wavelengths, but the luminosity, the visible luminosity. So let's go back to 3.85 times 10 to the 26 joules per second. In 1 year, we have 3.156 times 10 to the 7th seconds. And this tells us that in 1 year, this visible luminosity of the sun, 1.22 times 10 to the 34 joules per year. 1.22 times 10 to the 34th joules per year. Now we're going to drop into E equals mc squared. We have the energy amount over here. We want to calculate the mass, how much the mass is being rearranged into visible luminosity, into joules, and we'll use the speed of light squared, of course, so E equal mc squared, if I remember to get the C on there. So E equals mc squared. We've got 1.22 times 10 to the 34 joules per year. We're solving for the mass, the number of kilograms per year, and we have 3 times 10 to the 8th for the speed of light meters per second that has to be squared. Again, you should pause and do this on your calculator, but the mass converted to energy every year, I'm coming up with 1.35 times 10 to the 17th kilograms per year. 1.35 times 10 to the 17th kilograms per year. So our next question is, how much does the sun's mass decrease in 5 billion years? Suppose the sun has constant luminosity, constant energy production for 5 billion years. Let's just get kind of a scale as to how much mass decrease there is. So 5 billion years is going to be the fusion process is running and losing this much mass per year. So 1.35 10 to the 17th kilograms per year. We have 5 billion years. A billion is 10 to the 9th. And again, you should double check this on your calculator. 6.75 times 10 to the 26 kilograms. 6.75 times 10 to the 26 kilograms. And this is starting to become a significant amount of mass. How significant? Well, actually not that significant. If we compare this answer to the sun's mass, 1.99 times 10 to the 30th, you can already see we've got 10 to the 30th of mass. We're using 10 to the 26 kilograms in 5 billion years. But let's go ahead and do the division. 6.75 10 to the 26. 1.99 times 10 to the 30th kilograms. Both of these are kilograms. So we're just getting a comparison of how much does this mass compare to the total mass of the sun. And what we find is 3.39 times 10 to the minus 4. It's not a large fraction of the total mass of the sun. Now there's some things that are going to happen internally in the sun. The rate of fusion is going to change. We're not going to worry about those details. For those details, you should take an astronomy course and study the structure of stars. But we've accounted for fusion from the sun, each fusion reaction delivering a certain amount of energy. We converted that to joules. We've got the visible luminosity here. We did that division to find out how many fusions are per second. And then, it looks like a big number, but there's a lot of hydrogen in the sun. How much is the sun's mass decreasing in the air? Use the equals mc squared for that. And in 5 billion years, so we have the mass loss per year. So in 5 billion years, we get a value that is still a small fraction of the mass, total mass of the sun. So ask your instructor if you have questions about this.